This is the video abstract for the paper Quantum Bithreads and the Entropohedron by Matthew Hedrick, Andrew Rolfe, and me, Sriman. The new technical formula relates bulk geometry and boundary entanglement entropy. It can be reformulated in terms of Bithreads, which are divergences flows with a certain non-bound. Intuitively, it is similar to the fact that if water is going through a pipe, then the max flow is proportional to the minimum area, as it has to squeeze through the bottleneck. In this paper, we consider the static case, so we focus on a single Cauchy slice. There is a generalization of the RT formula called the quantum extremal surface formula for when the bulk matter is considered quantum rather than classical. The entropy of bulk matter, S bulk, is now included in the generalized entropy. Andrew Rolfe proved that the quantum extremal surface formula in the static case is dual to the following quantum Bithreads prescription. The non-bound remains the same, but the difference is that there is a divergence inequality constraint for all regions whose boundary is homologous to A. It is essentially an upper bound on the net number of sinks. This is an example of an optimal flow solution. The blue field lines give the area of the quantum extremal surface, and due to them, for the optimal flows, the non-bound is saturated on the quantum extremal surface, which is in green. The max flow finds any way it can get from A to A complement, and the divergence constraint allows quantum threads to jump across the classical bottleneck. The red field lines give the bulk entanglement entropy, and they saturate the divergence constraint for the entanglement wedge, which is the region R between the quantum extremal surface and capital A. Another example is a baby universe or a closed universe that is entangled with the two ADS spacetimes, and it has no boundary. Here, the left ADS bulk is entangled with the southern half of the closed universe. Threads are allowed to end in the left bulk because it has non-zero entropy, but they're also forced to reappear in the sphere's southern hemisphere because it purifies the left bulk. And also, the upper half of the closed universe is entangled with the right ADS spacetime. So they will again jump to the right ADS to end on the boundary. This is an example of an island setup. And for a similar reason as to the baby universe example, the threads are forced to reappear in the island because it partially purifies the region small a. Now the non-bound will be also saturated for the boundary of the island, and the divergence constraint is saturated for the entanglement wedge that now includes both the island and the region small a. We study the case of double holography in depth, and from that we motivate and prove that the quantum extremal surface is also dual to a slight modification of quantum Bithreads called the strict quantum Bithreads. The right figure is the boundary of the left figure. The S bulk term in the lower dimensional bulk causes the threads to jump. But in double holography, the S bulk is explained by the minimal surface in the higher dimensional bulk. If we also look at the higher dimensional bulk, the threads jumping due to S bulk actually go into the higher dimensional bulk. For the strict quantum Bithreads, the boundary of R no longer needs to be homologous to A. And the constraint is for all possible regions. And there is also a modulus. We also prove that some UV cutoff independent versions of Bithreads are equivalent to the quantum extremal surface formula, such as this one. S10 is better defined than either the areas or the S bulk separately. Here we have a single constraint instead of two. Entanglement is not a local phenomena, so it is not possible to define a precise local measure. We will define these entanglement distribution functions that are closely related to the Bithreads. For a continuous system, it is a local function integrated over some region A. And for discrete systems, the integration is replaced by sum. And for all regions A, it needs to satisfy the inequality. For the discrete degrees of freedom, x1, x2, and so on, if we plot all possible vectors f of x1, f of x2, and so on, we obtain the Entropohedron. For example, for a maximally mixed state, it looks like this. And for a maximally entangled state, it looks like this. It contains all the information about the entanglement of all subregions. And we studied the properties of the EDFs and the Entropohedron. Thank you for watching.